Welcome to Brain Vision.
Okay, so this is a data problem, so we need to do a really good job of having really nice rows and columns. And that will probably get extended later on. But anyway, here's our table. I think we actually need one more row. Ooh, that one's gonna be tight. Let's do that again. There we go. Okay, so I'm just going, these cars have names, but I'm just gonna number them 1 through 5. So these are cars 1, 2, 3, 4, and 5. Excellence, and then that's just the number, and then our first real column is going to be, sorry, not the force, the mass of each of these cars in kilograms. And those are very specific. So we have 895, 1320, 1435, followed by 1468. And then lastly, 1650. Good. Oh, kilograms, close parentheses. The second amount of information to us that's given is how long it takes, so delta t in seconds, for this model to accelerate from 0 to 60 miles per hour. They only gave this table to 2 significant figures. So that's 4.4 for the first car, 6.4 for the second car, 3.9 for the third car, 5.4, and then 7.2. So what we're interested in calculating for each of these cars is the force in newtons, because we need to determine which car has the strongest force and which car has the weakest force. So in other words, we're going to have to calculate all 5 of them in order to figure out what that is. So the basic of physics equations that we're going to be using is Newton's second law, of course. So that is mass being multiplied by acceleration. However, we're not explicitly told the acceleration, so really we're going to use the formula for average acceleration, which is delta v over delta t. This also gives us the impulse formula, for those of you who are familiar with that. So we know the masses, we know the times, and then we actually also know the delta v. We know that we're going from 0 to 60 miles per hour. However, that is not an SI friendly unit, so we're going to have to go ahead and convert that. So that actually gives us 27 meters per second, and then we will be all good to go to plug in this formula. So basically just do this calculation 5 times to fill in the data, treating it like a spreadsheet. So for our first value, when we plug in numbers, we get 5456. I'm going to report these to more significant figures than we probably should be doing, just because they gave us the masses so precisely. But it's not a big deal. We're just finding the largest and smallest values. Doing this 5 times, and then we get 7292 for this fourth one, and then capping it off with 6147 for the last value. And then for both parts A and B, we just need to basically identify which of these forces is the largest, and maybe I'll do it in a different color to highlight it. Which force is the largest, which one is the smallest. So car number 3 is our biggest force, and then car number 1 was actually our smallest force. And this is true for both parts A and B. So part A is asking for which car exerts the strongest force. So that's explicitly what we calculated in the third column. And then part B is asking if a person were sitting in this car, then which car would exert the biggest force and the smallest force. But it's the same for A and B because of Newton's second law, where it doesn't matter what the mass of the person or the car is. Once we've determined which one has the largest force, that one will also give rise to the largest acceleration. So that's what's going on in A and B. Moving onward a little bit, similar physics, but a slightly different answer. If we took the Jaguar car, if we took the Ferrari, which is the third car car, I believe. Yeah, if we took the third car and looked at the its acceleration from, instead of 0 to 60 miles per hour, from 0 to 100 miles per hour over this new given time interval. So let me write that all down. So our new delta V is 100 miles per hour, which if we do a unit conversion gives us 44.7 meters per second over some new time interval, because it's a new experiment of 8.6 seconds. Then what is this new force and how does it compare to the value in the table? So we literally just use the same formula again, which is F is equal to M delta V over delta T. Plug in numbers. So this is the Ferrari, so it has a mass of 1435 kilograms. Our delta V, we just said, was 44.7 meters per second, and then we're accelerating over a time interval of 8.6 seconds. So numerically, we get an average force of 7,459 newtons. And then this is smaller than the value in the table, which was almost 10,000 newtons. So this is smaller than the value we calculated earlier. And then the question wants us to postulate some reasons why. And then I'm actually going to answer parts C and D together to top it all off in the same explanation. So the faster a car goes, let's see how far my screen will go. The faster a car goes, the stronger the forces of kinetic friction and air drag. Just to be super explicit. Let's see if this does anything. Great. Okay. That specifically. Oops, lost my green. Resist the motion of the car. A car reaches its top speed when the force of the engine balances friction and drag. Top speed when So in other words, the net force is equal to 0. Okay, and that wraps up this problem.